Welcome back, friends. As I promised you in my previous video, that in this video we shall be discussing about the shapes of covalent molecules. So in introduction, we are saying that a type of hybridization gives geometry of a molecule. When the concept of hybridization combined with valence shell electron pair repulsion theory, geometric shape of various molecules and their bond angle can be described. So later we shall go to see about the valence shell electron pair repulsion theory. But before going to the valence shell electron pair repulsion theory, now let's first start or understand about the difference between the electron pair geometry and the molecular geometry. Now what are the electron pair geometry? Geometry kiufupi ni kama umbo la molecule. Sasa katika maumbo ya molecule yako aina mbili. Tunaweza kuwa tuna consider presence ya lone pair au tukaignore presence ya lone pair. Kwa hiyo ukichukua lone pair ukaiweka, if the lone pair is taken into consideration, hiyo inaitwa electron pair, kwa sababu hata lone pair nayo ni electrons. Kwa hiyo inaitwa electron pair geometry. Lakini lone pair ukizitoa ukaziweka pembeni, inayobakia inaitwa molecular geometry. Now we are saying that geometry of a compound or ion may be electron pair or molecular geometry. Electron pair geometric shape consider arrangement of all bonded and unbonded electron pairs, yani lone pairs in a molecule of a compound. So electron pair geometry considering both bonded and non-bonded electrons in a compound or in your molecule. So on the other hand, molecular geometrical shape or molecular shape considers arrangement of atom around the central atom. It considers arrangement of bonded electron pairs only, excluding lone pair. So I hope for these two definitions you have already understood that the electron pair geometry is the three-dimensional arrangement of all electrons. Electron pair geometry, three-dimensional arrangement of all electrons around the central atom, while the molecular geometry is the three-dimensional arrangement of atoms around the central atom. Does not consider lone pair. So molecular shape can be deduced by eliminating lone pair from electron pair geometry shape, leaving bonded electrons only. So electron pair geometrical shape only depend on type of hybridization. Electron pair geometrical shape only depend on type of hybridization. So by using the concept of hybridization only, we can know the electron pair geometry of every molecule. But before deducing the molecular geometry, we should remove the lone pairs from the molecules. So it is not affected by the presence or absence of lone pair. It remains the same provided that the type of hybridization remains unchanged. So all molecules with the same type of hybridization will have the same electron pair geometry shape. But molecule with the same type of hybridization, if they have different number of lone pair, they may have different molecular shape. This is different to the molecular geometry, whose shape and bond angle depend on the number of lone pair. So molecular geometry, shape and bond angle depend on number of lone pair, where the bond angle of molecule decreases with an increase in number of lone pair. Bond angle of molecule decreases with an increase in number of lone pair. The decrease in the size of bond angle as the number of lone pair increases is due to the increase in the repulsion of lone pair bonding pair electrons compared to the. So according to this statement, as I told you in some of my explanations before, that for example, if you have sulfur dioxide and then you expect the structure of sulfur dioxide could be like this, the two lone pairs in sulfur, they tend to push the electrons, because even these bonds, they are bonded electrons. So the lone pair, they push the bonded electrons, and then the structure of sulfur. The structure of sulfur becomes like this. Here I think there is only one lone pair. Becomes like this. So why does this become like this? Because of the presence of lone pair which tend to push the bond electrons. So in short, we can say that the electron pair geometry and molecular geometric shape, it is the same if the molecule does not have lone pair. But presence of lone pair, they cause the shape to change. Now let's take the example here. Since the type of hybridization of boron in boron fluoride is sp2, trigonoplanar hybridization, its electron pair geometric shape will be trigonoplanar with bond angle of 120. So for example, this is the shape of boron fluoride, and as you can see here, its shape looks like this. Now, on the other hand, molecular geometric shape is deduced from the electron pair geometrical shape after eliminating lone pairs. For beryllium fluoride case, there is no lone pair in boron, so therefore nothing will be eliminated to get its corresponding molecular geometrical shape. So the molecular geometric shape will remain the same. So for example, here is the case of the boron fluoride, but in some of the cases, let's see some of the cases here, that in absence of lone pair, electron pair geometric shape is equal to the molecular geometric shape. Now what happens when there are lone pairs? What happens when there is or when there are lone pairs? First, some lines will not appear in the molecular geometric shape compared to those present in the corresponding electron pair geometric shape as a result of the elimination of unbonded electron pairs from the electron pair geometric shape. Now remember, molecular geometry consider bonded electrons paired only. Secondly, the bond angle will be distorted because bonded and non-bonded electron pair exert different repulsion. This means that in the presence of lone pair, the molecule can no longer symmetrical, it becomes asymmetrical. Now consider our example is sulfur dioxide, and the hybridization is sp2 hybridization, and therefore its electron pair geometric shape will be trigonoplanar. sp2 is trigonoplanar. Now after elimination of the lone pair in the above electron pair geometric shape, molecular geometric shape obtained will be bent shape because this pair is removed. This line and this line will not be seen, so we will remain with only these two pairs of the electron, and the shape of sulfur dioxide will appear as this one, as you can see in the diagram. So in the above case of the molecular shape, the bond angle is no longer 120 because the lone pair and bonded electron exert different repulsion. In fact, it is slightly less than 120 because the lone pair exert stronger repulsion than bonded electron, as will be explained by the valence shell electron pair repulsion theory. Now note, something note, in geometry of covalent molecules, we are always more interested to understand the arrangement of atoms around the central atom, and therefore when you are asked just to give the shape of the molecule, always give molecular geometric shape and not electron pair geometric shape. So if you ask about the shape of the molecule, just mention the molecular shape rather than the electron pair geometric shape. So let us end up here, and in the next lecture we shall finish with the valence shell electron pair repulsion theory and all of about the shapes of molecules, and we will solve some of the questions on this topic of general chemistry. of nice studies. Subscribe the channel and share the link for more updates and to share the knowledge with your fellow students. Thank you.